In this video, I want to introduce you to something called a Lagrange multiplier. We use Lagrange multipliers when we're working with constrained optimization problems in two independent variables. So a constrained optimization problem are those where two or more conditions, which I call constraints, exist that can each independently affect the final output for a specified objective function. The key to solving these kinds of problems is to first identify the function that is being optimized, and that's the one I call my objective function. We've actually worked with these back in algebra, where we graphed them and found the vertices and computed the maximums and minimums, but calculus makes this a little bit more elegant and streamlined. If I have an objective function in two variables, I require that the function be differentiable in x and y, and I require x and y to lie on what I call a constraint curve, C, in the xy plane, given by g of xy is equal to 0. So a picture of this would show a surface that lies above my xy plane, given by z is equal to d of xy, but my constraint curve C is the projection of that boundary region onto the xy plane itself. This constraint curve is given by g of xy is equal to 0. So when I solve these constrained optimization problems, I need to not only identify the objective function, but we need to identify the constraint curve, C, which is all xy such that g of xy is equal to 0. I want to use the first partial derivative of my objective function f of xy in order to identify critical points. Once I've identified those critical points, I know that a maximum or a minimum value may be located at one of those critical points on the constraint curve. So for a given constraint curve, we can identify a level curve that will intersect the constraint curve at a critical point AB. And this means that we can think about the constraint curve as just another level curve for our function, and therefore the gradient of the constraint curve will be orthogonal to the constraint curve itself at the critical points that we've identified. We are going to assume that the gradient of g at AB will not be 0 here. Now, since the gradient of f at AB and the gradient of g at AB are both orthogonal to the level curve, this means that the gradient of f at AB and the gradient of g at AB are parallel, and parallel vectors are different only by a scalar multiplier. So I can say that del f of AB is equal to lambda times del g of AB, or the gradient of f at AB is equal to some scalar lambda times the gradient of g at AB. This scalar multiplier, lambda, is a real number scalar, and we call it a Lagrange multiplier. So now we're going to talk about parallel gradients, and this gives me the ballpark theorem. If we let f be a differentiable function in a region of R2 that contains the smooth curve C given by g of xy is equal to 0, assume that f has a local extreme value relative to values of f on the curve C at a point P with coordinates AB that lies on C. Then the gradient of f at AB is orthogonal to the line that is tangent to C at the point P. Assuming that the gradient of g at AB is not 0, it therefore follows that there exists a real number lambda such that the gradient of f at AB is equal to lambda times the gradient of g at AB. So the method of Lagrange multipliers involves just a couple of steps. If I let my objective function f and the constraint function g both be differentiable on a region of R2, with the gradient of g at AB not equal to 0, to locate the maximum and minimum values of f subject to the constraint that g of xy has to equal 0, we need to follow two steps. One, we first have to find the values of x, y, and lambda, if they exist, that will satisfy the equations given by the gradient of f at AB is equal to lambda times the gradient of g at AB, and g of xy has to equal 0. As I look at the values of xy that I found in step 1, the largest value I obtained corresponds to the maximum, and the smallest value I obtain corresponds to the minimum values of f subject to that constraint. So let's talk a little bit more in detail about level curves and constraint curves. The method of Lagrange multipliers only works at points where the level curve is tangent to the constraint curve. If I pick any other point on that constraint curve, the gradients will not be parallel. So let's work an example. I want to use Lagrange multipliers to find the maximum and minimum values when they exist of the function f of xy, which is equal to xy squared, subject to the constraint x squared plus y squared is equal to 1. I first take the gradient of f of xy. This gives me the vector with components y squared and 2xy. Then I have to make sure that the equation g of xy is equal to 0. I rearrange my constraint function to give me g of xy. I get x squared plus y squared minus 1 is equal to 0. Now I take the gradient of g of xy and I get a vector with components 2x and 2y. I know that the gradient of f has to equal lambda times the gradient of g, so that y squared has to equal 2 lambda x, which tells me that y is equal to lambda, which is equal to 0, giving me coordinates of plus or minus 1 and 0 for one of my critical values. I also know that 2xy has got to equal 2 lambda y, which tells me that x is equal to lambda. Solving y squared is equal to 2 lambda x for 2 lambda, and then plugging x in for lambda, gives me 2x is equal to y squared over x, or 2x squared is equal to y squared. I'm going to substitute 2x squared for y squared in my g of x function. This gives me x squared plus 2x squared minus 1 is equal to 0, or 3x squared is equal to 1, which tells me that x can be plus or minus 1 over the square root of 3. This gives me y is equal to plus or minus the square root of 2 over the square root of 3. The critical values will be plus or minus 1 and 0, 1 over square root of 3, plus or minus the square root of 2 over square root of 3, and negative 1 over square root of 3, and plus or minus the square root of 2 over the square root of 3. Now I have to evaluate the function values at each of those points. My function at plus or minus 1 and 0 is 0. My function at 1 over square root of 3 and plus or minus the square root of 2 over the square root of 3 gives me 2 over 3 square root of 3. The function value at negative 1 over square root of 3 and plus or minus square root of 2 over square root of 3 gives me negative 2 over 3 square root of 3. My function has a maximum value of 2 over 3 square root of 3 at the points 1 over square root of 3 and plus or minus the square root of 2 over the square root of 3. And it has a minimum of negative 2 over 3 square root of 3 at negative 1 over square root of 3 and plus or minus square root of 2 over square root of 3. So now you get to try it. Pause the video and use Lagrange multipliers to find the maximum and minimum values when they exist of the function given by f of xy is equal to x minus y, subject to the constraint that x squared plus y squared minus 3xy is equal to 20. When you're ready, restart the video to check your understanding. So I'm going to set this up and follow the same process. I first need to find the gradient of f of xy. My gradient of f at xy is given by a vector with components 1, negative 1. My g of x function is given by x squared plus y squared minus 3xy minus 20 is equal to 0. The gradient of g at xy is given by a vector with components 2x minus 3y and 2y minus 3x. The gradient of f has to equal lambda times the gradient of g, so I get the vector with components 1, negative 1 is equal to lambda times the vector with components 2x minus 3y and 2y minus 3x. This tells me that 1 is equal to lambda times 2x minus 3y, and negative 1 is equal to lambda times 2y minus 3x. If I add these two together, I find out that lambda times 2x minus 3y is equal to lambda times 3x minus 2y, or x is equal to negative y. Now I'm going to plug in x for negative y in my g function. I get x squared plus 3x squared is equal to 20. This gives me 5x squared is equal to 20, or x is equal to plus or minus 2. The critical values are going to be at the points 2, negative 2, and negative 2, 2. Now I have to evaluate my function values at those 2 points. F of 2, negative 2 is equal to 2 plus 2, or 4. F of negative 2, 2 is given by negative 2 minus 2 is equal to negative 4. The maximum value occurs at the point 2, negative 2, and the minimum value occurs at the point negative 2, 2. This is using Lagrange multipliers to determine the maximum and minimum values of an objective function subject to a constraint curve. Be sure and let me know if you have any questions.